In section 2, we're going to take a look at the Pythagorean theorem. But before we start talking about that, we want to review how we simplify square roots. So the way we simplify square roots is if we have the square root of a times b. So we're multiplying two numbers. We can break it down as the square root of a times the square root of b, where a or b is a perfect square. So we're looking for a perfect square that goes into our number. So remember, the perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. That's just the perfect squares for 1 through 12. There are obviously more, but these are the most common ones that I expect you to know, or / we will be using in class. So let's start by simplifying the square root of 96. So we want to be able to break it down as a perfect square times something else. So we can rewrite the square root of 96 as the square root of 16 times the square root of 6, because 16 times 6 is 96. The square root of 16 is 4, so we get 4 square root 6, and that would be our simplification. So we're looking at 6 times the square root of 8. So we want to break down 8, which is the square root of 4 times the square root of 2, but we still have the 6 out in front that's multiplying. The square root of 4 is 2, so it's 6 times 2 times the square root of 2, and 6 times 2 is 12, so we end up with 12 square root 2. Anytime there's a number already outside a square root, when you simplify that square root, you have to multiply it by the number that's there. So that leads us in our last example, -3 times the square root of 27. So we can rewrite the square root of 27 as the square root of 9 times the square root of 3, since 9 times 3 is 27. The square root of 9 is 3, so we get -3 times the square root of 3, which ends up giving us -9 square root 3. Sometimes it's very easy to figure out the perfect square that goes into a number. Other times it's a little bit more difficult. So that leads us into the Pythagorean theorem, which is named after a Greek mathematician named Pythagoras. However, there are records of it being used before him. So the Pythagorean theorem states that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the sides. So it boils down to a squared plus b squared equals c squared. And we are going to take a look at a proof of this. So in a right triangle, a and b represent the legs. C always represents the hypotenuse. So let's take a look at a proof. So the proof we're going to do has to deal with a square. Just imagine that this is a square. And inside that square, we are going to draw a second square that's kind of tilted, if you will, inside. Okay? And again, imagine that this is a square. And the point in this inside square, all of its legs, or all of its sides, have a length of c. And in the outside square, the smaller distances are a, and the longer distances are b. So we have this square where each side has a length of a plus b. So in our large square, its area equals the a plus b times a plus b, since the area of a square is side times side, and each side of the large square is just a plus b. We also have our small square, whose area is just c squared, since c times c is c squared. And then we also have these right triangles as well, because the square has all right angles. So in our right triangles, there are 4 of them. So we have 4 right triangles, and the area is 1/2 base times height, where the base is b and the height is a. So it's 1/2 AB, and there are 4 of them, which ends up giving us 4 times 1/2 is 2. So we end up with 2AB. So we know when we add the area of the small square with the area of our right triangles, we should get the area of our entire square. So that gives me that a plus b times a plus b has to equal the 2ab plus c squared. Now we're just going to distribute. So we do a times a to give us a squared. Then we do a times b, and it gives us ab. B times a, which is also ab. And b times b, which is b squared. Still equal to the 2ab plus c squared. Now on the left side, we have ab plus ab. So we end up with a squared plus 2ab plus b squared equals 2ab plus c squared. So we look, we have a 2ab on both sides. So we can subtract it from both sides, and we end up with a squared plus b squared on the left equals c squared. And we have just proven the Pythagorean theorem. And if we look at our right triangles that we have inside our large square, they have sides a and b and hypotenuse c. So we did prove the Pythagorean theorem using just squares and triangles. We also have something called a Pythagorean triple, which is a set of 3 positive integers, a, b, and c, that satisfy the Pythagorean theorem, a squared plus b squared equals c squared. So what a positive integer is, it's a whole number, so no decimals, no square roots, and they're obviously positive. So for example, we want to show that 3, 4, and 5 is a Pythagorean triple. So that would mean a squared plus b squared equals c squared. Now when you're trying to figure out, given 3 numbers, which ones are a, b, and c, the biggest number is always the hypotenuse, since the hypotenuse is always the longest side of the right triangle. So if I want to show this as a Pythagorean triple, we want to show that 3 squared plus 4 squared equals 5 squared. Well, 3 squared is 9, 4 squared is 16, and 5 squared is 25, and 9 plus 16 is 25, so we get 25 equals 25. So it is a Pythagorean triple. 3, 4, 5 is the most well-known Pythagorean triple. It is the smallest side lengths you can have that form a right triangle. So our next example, we want to show the 3 sides of the Pythagorean 3 sides of the triangle are a Pythagorean triple. So we want to find that third side C. So even though it's not labeled, our right angle is between the sides of 5 and 12. So it doesn't matter which side you label to be A and which side you label to be B. It doesn't matter which sides are A and B as long as they represent the legs of your right triangle. So we have 5 squared plus 12 squared equals C squared. 5 squared is 25. 12 squared is 144. So if 25 plus 144 equals C squared, 25 plus 144 is 169. So that equals C squared. So to solve for C, we take the square root of both sides and we get C equals 15. So we also have another Pythagorean triple, 5, 12, and 13. So if I have a triangle with lengths 5, 12, and 13, we know it has to be a right triangle. So in our third example, we want to decide whether the numbers are a Pythagorean triple. So we check to see that the two smaller numbers, when squared and added together, we get the larger number squared. So with 9, 40, and 41, we're checking to see that 9 squared plus 40 squared equals 41 squared. 9 squared is 81. 40 squared is going to be 1600. And then 41 squared is 1,681. So when we do 81 plus 1,600, we get 1,681 equals 1,681. So the answer is yes, 9, 40, and 41 are a Pythagorean triple. Next, we're going to take a look at 10, 49, and 50. So we want to check to see that 10 squared plus 49 squared equals 50 squared. 10 squared is 100. 49 squared is 2,401. And 50 squared is 2,500. So when we do 100 plus 2,401, we end up with 2,501, which does not equal 2,500. So in this case, no, 10, 49, and 50 are not a Pythagorean triple. They could form a triangle, they just do not form a right triangle. So now we're going to find unknown side lengths using the Pythagorean theorem and then determine if the lengths form a Pythagorean triple. So in our first example, we have sides x and 9 and hypotenuse 11. So doesn't matter which one we choose to be x and 9 for a and b. We can set up as x squared plus 9 squared equals 11 squared. So we get x squared plus 81 equals 121. We're going to subtract 81 from both sides. So we get x squared equals 40. Now 40 is not one of our perfect squares on the front. So I already know that our side lengths are not going to form a Pythagorean triple. But we're going to go ahead and take the square root and simplify anyway. So we get x equals the square root of 40. We do want to simplify our square roots if possible. So I know that 40 is the same thing as 4 times 10. So I can write it as the square root of 4 times the square root of 10. And we get x is the same thing as 2 square root 10. And because 2 square root 10 is not a whole number, it is technically a decimal, this is not a Pythagorean triple. The three sides form a right triangle, just not a Pythagorean triple. So in our second example, we have legs with lengths x and 10 and hypotenuse of length 20. So plugging into the Pythagorean theorem, we get x squared plus 10 squared equals 20 squared, which becomes x squared plus 100 equals 400. We're going to subtract 100 from both sides, and we get x squared equals 300. So we take the square root of both sides, and if you try, you're going to get the square root of 300 as a decimal, which means it's not a perfect square. So x equals the square root of 300, which is not a whole number, which means our sides do not form a Pythagorean triple. But we can simplify the square root of 300. Because 100 is a perfect square, and 100 times 3 is 300. So it's the square root of 100 times the square root of 3. So we get that our missing side has a length of 10 square root 3. So again, we have not a Pythagorean triple. we have two more examples. So in example 3, again, we have the legs of lengths x and 8 and our hypotenuse 12. So x squared plus 8 squared is going to equal 12 squared. So we get x squared plus 64 equals 144. We're going to subtract 64 from both sides, and we get x squared equals 80. We're going to take the square root of both sides, and we're going to end up with a decimal, so x equals the square root of 80, which we want to simplify. And while 4 does go into 80, it is not the biggest perfect square that goes into 80. 16 is, so we can write it as the square root of 16 times the square root of 5. So we get that x equals 4 square root 5. So again, not a whole number. So again, we have not a, I'm going to abbreviate Pythagorean here, not a Pythagorean triple. One last example. We have, this time, the legs have lengths 4 and 4 square root 3, and we want to find the hypotenuse x. So I already know that my 3 sides are not going to be a Pythagorean triple, because one of my sides already has a square root in it, which is not a whole number. So right off the bat, we know we won't end up with a Pythagorean triple, but we still want to solve for our missing side. So we get 4 squared plus, we want to put 4 square root 3 in parentheses, and then squared equals x squared. We want to make sure that when we square 4 square root 3, we put the entire thing in a set of parentheses. So we end up with 16 plus, and then if you use your calculator to square 4 square root 3, you're going to end up with 48. Make sure you put parentheses around it in a calculator. Equals x squared. 16 plus 48 is 64. Take the square root of both sides, and the square root of 64 is a perfect square. It is a whole number. We get x equals 8. But as I already said, we already knew one of our sides wasn't a whole number, so we already know it's still not a Pythagorean triple. So in our example 5, we have that a baseball diamond is a square with sides of 90 feet. We want to know what is the shortest distance to the nearest tenth of a foot between first base and third base. So if we were to draw a baseball diamond, which is a square, we know each side here is 90 feet. We have home base, home plate, first base, second base, and third base. So the distance from first base to third base is that blue line, and it is in a triangle. We have a right angle at 2, which means the distance from first to third is our hypotenuse of our right triangle, which have legs of length 90. So we'll have 90 squared plus 90 squared is going to equal c squared. We'll go ahead and label the hypotenuse, that distance from first to third, as c. So 90 squared is going to be 8100. So we have 8100 plus 8100 equals c squared. 8100 plus 8100 is going to give us 16,200 equals c squared. We're going to take the square root of both sides, and we do ask for a decimal to the nearest tenth of a foot, because the square root of 16,200 is not a whole number. But when we do the square root of 1600 in a calculator, 16,200, we are going to get 127.3 feet. The decimal is 0.279, but because this asks us to the nearest tenth, which is 1 decimal place, we look at the 7, which is going to round up that 2 to a 3. So we get 127.3 feet. In our very last example, we have that 2 joggers run 8 miles north and then 5 miles west. What is the shortest distance to the nearest tenth of a mile they must travel to return to the starting point? So we're going to have, there's our starting point. We run north 8 miles, so we'll call this 8 miles. Then they go west, which is directly right, 5 miles. Sorry, directly left. Okay. Then we want to know the shortest distance to get where they started. So that does create a right triangle, and our shortest distance is our hypotenuse C. So we set up our Pythagorean theorem. We're going to have 8 squared plus 5 squared equals C squared. 8 squared is 64 plus 5 squared is 25 equals C squared. 64 plus 25 is 89. We're going to take the square root of both sides. So when we take the square root of 89, we're going to get 9.433, but the nearest tenth of a mile is 1 decimal place. So we get 9.4 miles, because the 3 does not make the 4 round up. As always, let me know if you have any questions as you're working on the assignment.